Welcome to another Math 30-1 lesson in Chapter 5 as we're looking at exponential and logarithmic functions. And we're on to Section 6 of the chapter where we're going to analyze logarithmic functions. So here we're going to be looking at the graphs of logarithmic functions and seeing again how we can apply all those transformations that we learned previously in the course to graphs of logarithmic functions as well. But to begin with, we have some warm-up questions here. So you'll see these first 4 questions where we're just going to practice rewriting these in logarithmic form. Question number 5, I'd like you to do this without a calculator. Can you identify which graph A, B, C, and D matches which equation that we have on the right? And then you can skip this note. We'll fill that in a moment. And go on to number 6 and 7. Just evaluate these 2 logarithmic expressions. All right, so you can pause the video at this point and then restart once you've finished this page. Well, I hope there wasn't a whole lot of challenge, at least with these first 3 questions. As we look at question number 1, remember in exponential form, here we have our base is b, the exponent is 0. So if we're going to write it in logarithmic form, then we write a logarithm with the same base of b. Remember that the logarithm is an exponent, so it's equal to 0, and it operates on the power. And here we said the power, b to the 0, is equal to 1. So log base b of 1 is equal to 0. Number 2, similar idea. As I look at the left, my base is b, so I have log base b. It's equal to the exponent of 1, and it operates on the power, which is the b from the right-hand side. And then here's a more generic expression. Again, I have a log base b. It's equal to an exponent, and it operates on the power. And here we're saying x is equal to the power, where b is the base. Number 4, basically the same idea. So if I just kind of look at where I place things, here my base is b. So I have the log base b, and this is equal to the exponent, which is log base b of x. So this entire exponent up here is what's going on the right side of my equation, and this logarithm is operating on this x. So I get log base b of x equals log base b of x. Well, yeah, that's true. And that's just a reminder that here, this exponential expression, b to some exponent, and then the logarithmic operation, log base b of something, because they are inverses, they undo each other. So we saw this a few lessons back. And we'll summarize that. Well, let's come down here to summarize that at this point. So again, note that y equal b to the x and y equal log base b of x are inverses of each other. And that helps us with number 5 as well, because we can see that the graph for A and the graph for D are going to be reflections in this diagonal line y equals x, which means they are inverses of each other. So roughly diagonal line there. And hopefully you remembered that the larger my base is, so this base of 10, the more quickly an exponential function grows. So graph A will match the y equals 10 to the x. B, that also will be an exponential function, so that'll be the base of 2. And then as I look at the reflections in that diagonal line, B and C will be inverses, so C will be log base 2 of x, and then B will be the log base 10 of x. We'll look more at graphs as we go through today's lesson. As you did question number 6 and 7, hopefully you could just plug them into your calculator and you discovered, dum, da, da, dum, you get exactly the same answer. Well, that illustrates the change of base rule for logarithms, which is here if I have, let's switch color here, if I have a log base 5 of 4, I can rewrite this as the log of 4 over the log of 5. Now here, both of these are base 10, but it is true for any base. So here, if I have log base b of c, this will equal to the log base whatever, so I'm going to say base a of c, divided by the log base a of b. Now typically when we're going to use this rule, most of the time we're going to use our base to be a 10 for the common logarithm because that's something that all of our calculators can operate in. So some of your calculators will work in different bases, like number 7. You can actually enter this base of 5. Some of yours may not, in which case you need to use this law of logarithms in order to evaluate. But you can always do it with a base of 10. Another option would be to use the base of e, in which case you would have the natural logarithm of c over the natural logarithm of your b value. Well, why does this law of logarithms work? Let's have a look here at doing a proof for this. And once again, we're going to start by saying that log base b of c, let's just say that's going to equal x. And we put on these restrictions on the b value in order for our logarithm to be defined. Well, let's take this logarithmic equation that we have here and rewrite it in exponential form. So log base b means my base is b, a logarithm is an exponent, so my exponent is x, and this will equal c. Now I'm going to do something that we haven't done before, but I'm going to treat a logarithm as a mathematical operation. So whatever I do to one side, I have to do to the other side. So I could square root the left side and square root the right side, and I'd still get a true statement. I could cube the left, cube the right, and still get a true statement. What I'm going to do instead is I'm going to take the log base a of the left side and the log base a of the right side as well. And again, because I'm operating on equal things, my left and right side will have to be equal to each other. Well, using the laws of logarithms, where I have that b to the x, I can take that x from the exponent and multiply it out in front. So I'll have x times the log base a of b is equal to the log base a of c. So now, as I continue with this equation, using rules for equations, I can divide both sides by this logarithm, log base a of b, and I can divide it by log base a of b on the right as well. But remember, I can only divide if my denominator is not 0. Well, what value for b would make my denominator 0? Well, let's just go over to the side here. Log base of a to the 0 is equal to 0. So if b was equal to a to the 0, or if b was equal to 1, then I couldn't make this statement. But as we look back up here, I already reminded myself that for a logarithm and exponential function, my b value can never equal 1. So I know that my b value can't be 1, which means b can't equal a to the 0, which means that log base a of a to the 0, or log base a of b, can't equal 0. So I'm not dividing by 0. I'm performing a legal operation here. That gives me x is equal to log base a of c over the log base a of b. Well, where did we start this question? We started by saying, well, let's just suppose that the log base b of c is equal to x. So this is equal to log base b of c. And we have proven this law of logarithms. Let's look on to the next page. Here we have a couple examples, and just for practice, we want to evaluate these, writing them as base 10 first, then evaluating. So using that law of logarithms, this log base 5 of 50, I can rewrite as, so what helps me remember is the number that's lower down is going to be in the denominator, and the number that's higher up will be in the numerator. So I'll have the log of 50, and since I'm looking at base 10, I'm not going to write the base in, it's a common logarithm, over the log of 5. And that's something that we can just type into our calculators to evaluate. And when we do, we get approximately 2.43. Number 9, similar idea. I can rewrite this as the log of 6 divided by the log of 8, and then evaluate. And I get approximately 0.86. Now, just a point of observation here, that here, if I'm taking the logarithm of a larger number divided by a logarithm of a smaller number, I will get a result that is larger than 1. And here, if I do the logarithm of a smaller number divided by the logarithm of a larger number, I get a value that's less than 1. Just to observe. All right, we want to complete this chart to describe the transformation. So I've called this an example, but I think you should be able to do it again as you think about what each of these different elements do to the logarithmic function. So if I have a negative sign out in front, what does that do to my logarithmic equation? Well, that'll be reflection. It's out in front, so it's changing y values, which means it's a reflection in the x-axis. So it changes y values. So as I look at my table here, this y value that was a 0 will stay a 0, but my x is unchanged. Here, my y value of 1 will change to a negative 1, and here my y value of y will change to a negative y. So what I'm going to get down this column will be a mapping notation, where this xy, in this case, will get mapped to x comma negative y. Now for the original function, we didn't fill in these last 3 columns, but just a reminder that a logarithmic function has a vertical asymptote at x equals 0. The domain is x is greater than 0, and the range is all real numbers. So as we look at this reflection, y values were changing, x's stay the same, which means my asymptote and domain and range, none of those have changed. Why don't you pause the video at this point and continue filling in the table, and then once you're done, or once you feel like you need some explanation, then restart the video and follow along with me. So you can pause the video now. All right, the next stage, we still have the negative in front. So any change that happened in the previous line will carry down to this line. But we also have this 2 here that's multiplied to the x. So that tells me that I'll have a horizontal stretch by a factor of 1/2. So this x-coordinate times a half gives me 1/2 for the x. The 2 times a half gives me a 1 for the x. And the x times a half gives me a half x. This asymptote, when I do that horizontal stretch, doesn't change the location of the asymptote because it was right along the y-axis, which means my domain hasn't changed either, and neither has my range. Next feature we have is we have this +4 grouped inside with the x. So that tells us it's going to move to the left by 4. So all the x coordinates will decrease by 4. So I'm going to take this 1/2 and I will subtract 4 to get my new x coordinate, which is a -3.5. That is a 2 in the denominator, a little messy in how it's written. If I do 1 minus 4, I'll get a negative 3 for the x. And a half times x minus 4 gives me the mapping for that x coordinate. So now that I've shifted the graph to the left by 4, that's changing the location of my vertical asymptote, and it's changing my domain. Range, still unchanged. Finally, we have this plus 3 that's added on the end. That will be a vertical translation. So that's going to change y values. So now I'll take this y value of 0, and since the graph moves up, I will just add 3 to the y value to get negative 3.5 comma 3. Add 3 to the negative 1, that'll give me a 2. Add 3 to the negative y, and that gives me the mapping for this entire transformation, where I have the reflection, the stretch, the horizontal and vertical translations. When I changed it vertically by translating up and down, that doesn't change my asymptote or my domain or my range because my range was all real numbers. So this is very similar to what we did back in chapter 3. So now we want to graph the two functions on a grid over here. So here we have 4 points. The first 2 points are in our table up here, the 1 comma 0 and the 2 comma 1. The next 2 points, we can use the mapping that we discovered from this point up here to figure out what our new xy ordered pairs will be. Well, the first 2 we already have because we did them in the table above, so I'll just drag those out. Here, if I take this 4, multiply it by half, I get 2. Subtract 4 will give me a 2. And take the negative of 2, so I have a negative 2 plus 3 will give me a 1. So my ordered pair, negative 2 comma 1, and I can do the same thing with the 8 comma 3. So what will our graph look like? Here, I've only sketched the graph of the transformed function. The original function will have gone through, I'll just plot some of those points. So we have the 4 points from the original function. I'll plot them, but I won't sketch the curve because it'll just be ugly if I try. So we had 1 comma 0 and 2 comma, whoops, 1 comma 0 should be here. Look at the scale, be careful. And then 2 comma 1 is a point here. 4 comma 2 gives me the point there. And then 8 comma 3 was the point up there. So originally my curve came down like this with a vertical asymptote along the x-axis. So there have been some points here approaching the y-axis, I should say. All right. Here we have a table to summarize. Again, you could fill in all this, so I'd encourage you to pause the video at this point, fill in the table, and then restart the video once you have filled in all this information. Here's what I have. Again, take note that in my 2 equations from chapter 3, we used a b value here, but because my base is b over here, I've chosen to use the letter or the variable c. So here I have the c is greater than or less than 0 for the reflection in the y-axis. And similarly, I have the c showing up here. But we're really just applying all those bits of the transformation now to a logarithmic function, which leads us to a few check your understanding questions. So try 11 and 12. What would the domain be for each of these? And again, I would encourage you to try this without using your calculator. What is the domain for a regular logarithmic function, as in y equal log base 4 of x? And then what's happening with the transformation? How does that change the domain? So pause the video now, restart it once you finish number 12, and then we'll have a look at number 13. Well, the domain for the untransformed function was x is greater than 0. So anything that's inside the logarithmic function has to be greater than 0, similar to when we have a square root function, then it could be greater than or equal to 0. Now we can't equal 0. It has to be just greater, and I rearrange to solve x is greater than 3. Similarly for number 12. If I start by rewriting, so I factor out that negative, then I can say, well, everything inside my logarithm has to be greater than 0, go through and solve, and we get x is greater than 3, which looks like a heart. Now, did you have to factor out this negative in order to find the domain? No. I just chose to do it this way, kind of as a reminder that when we have a negative coefficient in front of our x, we need to factor it out to understand that this graph is actually translated to the right by 3 units. Try number 13, which is a check understanding your, apparently. When you finish, again, restart the video and compare. Well, to help me with this transformation, what I did was I created this mapping here. So there's nothing multiplied inside the logarithmic function, which means there's only a translation to the left by 4, which moves that vertical asymptote to y equals -4. And then I could take each of these points, so you can see the green, blue, red, and yellow on this original function here of y equals log 1/2 x. So that's what was originally graphed here. And then I perform the transformation. So each point is left 4. So the blue, left 4, red, left 4, yellow, left 4. And then for the y coordinates, we have that vertical stretch by a factor of 3 and then up 1. So let's just look at this yellow one. It was at a y value of -3 times 3 is a -9 plus 1 takes it up here to a -8. So left 4 and then stretched vertically by a factor of 3 and then translated up 1 unit. That is the end of this lesson. So here are some questions for you to practice from your workbook. And we have 2 lessons to go in this chapter. See you in the next one.